we are going to talk about Newton's second law in polar coordinates, and we will try to give an example on why it's a good idea to study these kind of things. Well, let's start by polar coordinates, where we know that they are given by simple sine and cosine functions, and the first thing that we want to do is to consider, let's say we have a point P here, and this point is going on the circle. What we're gonna do is to give a unit vector in the r direction and the unit vector in the rotational direction, and this r vector is the unit vector in the direction of r, as we can see, while phi is fixed, and the phi direction is the phi unit vector is in the direction of phi, while radius is kept fixed. Now let's see what happens. When you have a point P which moves after some times come to a point Q, and this is the angle here. So it's gonna cover this distance delta r here. So we want to know what is this delta r. Well, the first thing that we can do is we can write this delta r as an approximation, where delta r in units of direction. Delta r can be approximately written as delta phi in the phi direction. So the change in r can be written the change in phi through the direction of rotation, which can be approximately written as phi dot delta t in phi direction, because this is moving after some certain time. This is t1 and t2. Now if you take the limit of delta t going to 0 of delta r over delta t, you are going to get the derivative of the unit vector with time. It's going to be phi dot in the phi direction. So this is one of the equations that we are going to need. This is one of the equations that we will need later. Next is that any vector r, so this is a vector r, can be written as r times the unit vector, where the unit vector r, you can think of it as I, j, k, for example, when you learn in linear algebra, and same goes for phi. Therefore, you can come to the conclusion, you can prove that d phi hat over dt is minus phi dot minus phi dot in y direction, in r direction. So these are two equations that we need later. Why do we need? It's that when we find the derivative, we have to find the derivative of the unit vectors too. Now when you write the velocity, you have d r vector over dt, d over dt of r hat, which is going to be r dot in the r direction plus r, the derivative of phi with respect to t, and the velocity can be written as r dot r hat plus r, and here is where you need this equation. You plug it in and then you're gonna get phi dot in the phi direction. So this is the velocity in polar coordinates, and we can continue to find the acceleration, which is dv over dt, and this is going to be d over dt of r dot in the r direction plus d over dt r phi dot in the phi direction, and this is, so dt by d r dot is r double dot in the r direction plus r dot dr by d phi, well, here it's a mistake, here is dr by dt is phi dot in the phi direction plus d over dt of r phi dot in the phi direction plus r phi dot in d phi over dt. And here, so this derivative can be written as r dot phi dot plus r phi double dot. Therefore, for the acceleration, we are going to have r double dot minus r phi dot squared in the r direction plus r phi double dot plus 2r dot phi dot in the phi direction. So this is the acceleration in polar coordinates. Now what we need to do is to write Newton's second law, where Newton's second law is just F equals ma, and you can write it as Fr, so force in the radial direction plus the force in a rotational direction, and this is m r double dot minus r phi dot squared, and f phi is m r double dot plus 2r dot phi dot. So this is the Newton's second law in polar coordinates. And now we can come with an example. Let's suppose that we have a half circle like this, and we have a skateboard here. So here is the radius of this half circle r, and we want to know what are the equations of motion. So what we are going to do is we have to balance the forces here. We have to first see what are the forces that act on this body. Well, first we have the weight of the skateboard. and so here this is phi. Yep. And second, we have a normal force that is acting on the skateboard. So these are the two forces that act on the body, and we suppose that we do not have a frictional force. The next thing that we have to do is to decompose the forces on the radial direction, which let's call V, so the weight in the radial direction, and the weight in the rotational direction. Here is the angle phi. We can find that sine of phi is equal to weight in the phi direction over mg. Therefore, w phi is mg sine phi, and cosine of phi is given by Vr. I keep calling it V, but it's just a WR over mg. So the weight in the radial direction is mg times cosine phi. We take that this is the direction of plus r, so this is the positive direction of r, and this is the negative direction of rotation. So clockwise is negative. Now what we need to do is just to balance the forces that act on the body. So basically we have that, so all forces acting on the body should equal F equals MA. In our case, F equals MA can be decomposed into FR and F phi, and we can write minus M. So what are the minus M? Minus M R double dot, minus R phi squared, and the other is M. Oh, sorry, here is M. R double dot, R phi double dot, plus 2R dot, phi dot. Going furthermore, we have that R is equal to R constant. So the radius of this half circle here, so this radius here, is a constant. And when R is a constant, we have V and A, VR and AR, we call R0. So you have no velocity and acceleration in the radial direction. Therefore, here R double dot is equals to 0, so R double dot is equals to 0, and R dot equal to 0 too. So FR is going to be minus M R phi. Let's write it with a big R, R phi dot squared, and F phi is going to be M R phi double dot. So in our case, we have no velocity and acceleration in the radial direction, just in the rotational direction. Now we need to balance the forces. Let's start with the radial component. Well, if we start with the radial component, so these are normal to each other. I didn't write well, but these are normal. We focus here. So we have the weight in the radial direction, which is going to be, so the weight in radial direction minus the normal force are going to compensate for minus m r phi dot squared. This is for r. And VR, we have here VR, which is mg cosine phi minus n equals to mr phi dot squared. This is for r. While for rotational direction, we have to concentrate here. So we have the force, the weight in the radial direction is this one, and we have no other forces acting. So we have v phi equals to mr phi double dot, where w phi is mg sine theta sine phi mr phi double dot. So the masses cancel, and we get to I guess we already know this equation, phi double dot, where it should be, I think, it should be here. Well, the minus there is good, but the minus is on this side of equation because this is the negative. So we said that here is the negative direction of the rotation. So we have minus the weight on the phi direction. So we have minus the weight in the phi direction minus mg sine phi equals to mr phi double dot, which is going to give phi double dot minus g over r sine phi. This is for phi. So these are two equations of motion that we need to solve. We need to solve to find just a phi of t. So what we are looking is a phi of t. Well, and luckily we just need one equation, and this is the second equation here for phi. And we are not going to solve it completely because you can solve it completely, but it requires knowing of you need Jacobi elliptic functions. Here we are not going to use those kind of functions, but we are just going to approximate for small angles. For small angles phi, you can approximate the sign by with the angle. Therefore, we come to the famous equation, which I think most of us know, which is the equation of motion for pendulum. And you can solve this equation by proposing a function phi of t, a times sine omega t plus b times cosine omega t, where omega is the frequency, g over r. And from this you can find that the period of oscillations is 2 pi over omega, 2 pi r over g. And if you have a radius, let's say r equals to 5 meters, therefore you can find that the period of the skateboard going from, let's say, to a point A and coming back is going to be 4.5 seconds. So yeah, so this is the example of using polar coordinates for Newton's second law